Hello, everyone. Welcome back. I hope you're well, and I hope you now managed to go through all the work and ready to continue. So far, so good. I hope you are coping and you haven't been overwhelmed. I haven't given too much work for my part of the course, and I've been trying to prepare as much content for you to be able to learn as much as you can. So far, we have managed to learn linear programming using graphical. We have managed to learn linear programming, started Simplex method, and managed to do some question, and they have had a tutorial and such. So today I want to just try to start a new thing, but I have done a very thorough work in preparing enough examples with step-by-step raw operation on how you should go about solving the Simplex method questions. And even on the big M method, I have as well added a lot of questions with solutions. So I try to actually do them stage by stage, and you should be able to follow through. So the bigger thing is, or the bigger job is on you to just now try to read these notes, follow through, and try to make sure that you actually get the solution I'm getting. And I know, as always, there will be some errors. Of course, I'm not like a superhuman. There could be typos, and I'm very grateful for those who came forward and tell me, Ezekiel, there are some typos somewhere, and I managed to correct them. So today, I just want to introduce you to the big M, and hopefully you will be able to understand what we are going to do, right? So as previously, as I told you, in this new notes set of notes, I have added more examples for Simplex method, and I remember last time I put the homework. So I hope that you have tried or you have attempted it, and you should get this. You should be able to get a solution. Furthermore, so I'm just going to give a little background, and then I can continue. So if you are given a minimization problem like this, you first transform it, i.e. rewrite like this, and then you introduce your slack variables. Of course, this is less than, so you introduce x3, x4, and then you put it in a tableau like this. And again, you look for what? You look for the most negative number on the top here. So what is the number there? So if you read your initial basic solution, you just look when everything else is 0. So of course, what did you introduce here? You introduce x3 and x4. So that's one is 18 and 7. So that's why you have them, and this is your basic solution. Then you find the biggest negative, that is 6. Because that's a 6, then if you know the 6, then you know that it is this column where you are going to make whichever we're going to find the minimum ratio, i.e. you take 18 divided by 4, and then you take 7 divided by 1, and then you should get the minimum ratio. So if you try to find the minimum ratio, you should get that is the 4.5, which means we need to make this 4 to become 1, and everything else has to become 0 in that column. So you perform row operation, i.e. of course we want to make it, remember I said we have to make this one. So my row operation, row 2 star, i.e. my new row 2, it must have this row divided by 4 throughout. So that's what you get here, and you should get that, right? And then you perform other row operation. You use now this new row to make this other 2 rows zeros, right? i.e. row 3 is just now going to become row 3 minus row 2 star, which is my new row here. So I'm going to be using this row and then try to make the other rows equal to 0. So you should see that's the one. What we get here is what? This would have become a 1, and then everything else is what? Is a 4. So here there's a typo. It should have been 1, and everything else should become a 0. Right. Then from there, I look again for the most negative number, and then the most negative number is what? So the most negative number here, actually, yeah, sorry, I actually think this is correct. So because we are dealing with this, so this become 1, and then when you do the other row, it should become a 0, right? So if we perform the row operation, we should get them or everything else to become what? Everything else to become 0 here. So from here it was 6, it's become a 1, then you make it a 0, so it becomes a 0 and a 0. Next, we look for the most negative. It's going to be this one, of course. And then we look for the ratio. It's going to be that one, which means x1 is coming here, and x4 is leaving the basis, right? You do the row operation again, and you should perform this row operation, and you should get this. Now you should see that everything doesn't have any 0. So if everything in our top row is non-zero, then you know you have got a final solution. Now you can just read the final solution. Z is equal to 28. X1, when everything else is 0, is equal to 3. And X2 is equal to 3. And X1, when everything else is equal to 0, is equal to 2. And when you substitute those values in our equation here, it should give us a maximum or a minimum value, right? So for us, we got the minimum value to be 28. So homework, as always, there is more homework. And then unbounded now. This is I want to discuss this because this is important. Is what happened when your ratios all become non-positive, right? Remember all the ratios. When you do the row operation and figure that all your ratios are non-positive, it means that means you have an unbounded problem. Now remember in class we discussed that unbounded problem is if you could take an infinitely larger number for the objective function. So in this scenario again, in our equation we have an example here. You introduce x3 and x4 as our basis, and they're here as you can see. And then you read your initial basic solution. Then you find what is the most negative number. That's a -2. You find your row. Here you get it is a 2. Of course, the other one are nothing because it's negative numbers. Then you perform your row operation wonderfully as usual, and you see that. And what we get here is that the most negative number here now is -5. But see what happened. When you divide 3 divide by that, you get a -1. When you divide 2 divide by that, that's a negative as well. So those one, now my ratios are all negative. Now what that means is it signals you that that problem is unbounded. So remember that is very important. I.e. hint, what if also, this is a very important hint, you should remember that. So learn that. I put another example. I'm not going to discuss this because it's already here. And it has a wonderful row operation, what you're supposed to do, and you have a solution. So all you have to do is please do confirm that this solution is correct. I hope that you'll be fair enough on that. Another one as well. So this is another one where again it has all the row operation necessary, and the solution is here as well. So I hope that this will be clear and it will be enough example. Even further, there is another example, right? And this it has now 3 bases, and you should do that as well as practice, and you should get the solution. Even more, there is another one. So I think there are too many examples. This one it we go up to x6, and you should attempt that as well, right? Then the case for degeneracy. In a well-behaved linear programming, the basic solution corresponding to the successive step of the simplex procedure will always be positive. There are cases, however, in which one of the m basis variables becomes 0 at some stage of the calculation, so that 0 appear in the last column of the simplex tablet. The basis. So remember, I was talking about what happened when R become negative. Now, what happened when this B's become zeros? That's what a degeneracy is talking about. So in the following example, we will discuss. We see that no difficulty are met with transforming the first W in the second W, So there is an example here. We have this wonderful example I came up about to show you what is the degenerance story is all about. So the simplex criteria is not satisfied. So you'll see that if you formulate the equation, you are given this problem, you're maximizing that, subjected to this, actually subjected to that, you rewrite it in a canonical form as usual. Remember, it must be in a canonical form and it must be in a standard form. Those two things, they're important, remember. So if I put this in a simplex W, because it's already canonical, of course, here it is canonical and the standard, I will then get this. Now I'm gonna look for a most negative. It's gonna be that. So the ratio is 1 divided by 1 and then that. So I should get that. So the smallest ratio is that, right? We proceed to update the W by performing the following row operation. You do that again. We obtain the following W after performing the row operation. If we go ahead and find the most negative element in the top row and the minimum, again, we obtain the following W. So we get this, right? So after getting this is now, we get this again and we look now for the most negative element, right? So again, what will be our most negative element? Ignore the row here, the arrow here, it shouldn't be there, it should actually be that one, right? X1. So if we check again, you see that, so we see that if we choose, we have a problem because here we actually have a 0. Now that's, when you have a 0, that's a problem because you're gonna have to get a degenerance, because it means from here, what should we have chosen? Should we have chosen, now remember the ratios are the same, so should we have chosen row X4 to leave or X3 to leave, right? Let us first start by choosing X3 leaving the basis and X2 leaving entering the basis. We perform the following row operation, you get that, and you see that you get a 0. We see that the simplex criteria is not satisfied, so we instead enter X1 as a degenerance. So X1, we enter it as a degenerance, right? It has a negative value there, and we try to perform and make it equal to 1. Again, by doing that, we see that here the simplex criteria is satisfied, i.e. the first basis solution is optimal, you have that. The reader will have perceived that the basis solution of W3 and 4 are identical in each case. In either case, we have a degenerate solution in one positive variable. All other variables are equal to 0 and make no difference to the solution whether one of them, no matter which one, is formally considered as a basic variable having the value of 0. So you see, you could have chosen either of them. You could have chosen X1 to be 0, X3 and X4. All of those, the only value which is a proper solution here is X2, which is here. Everything else is 0. So that is an issue where you might encounter sometime, right? It's actually very difficult to get degenerance. So degenerance then occur when the effective limit to the new basic variable is set jointly by several variables, i.e. when you have this scenario, then you know that there is degenerance in your equation have a degenerance issue. Remember, when these things are non-negative, your problem is unbounded. When they are the same, then you have degenerance where one variable has to be equal to 0. All right. Okay. So again, you should read the notes and practice this. In the next part, I want us to briefly start what's a big M, but i.e. these are the notes which I've already discussed by having a lot of examples. So I'm not going to discuss them. And you have actually, some people have already read this. So, and I haven't even put the row operation you're supposed to perform to get them. Right. Okay. So what else? Now we move to, I have already talked about unbounded. Now, the next thing I want to talk about is an alternative optimal solution. So remember, alternative optimal solution was in the graphical method. We say that alternate solution happens when you have one of the constraints having the same slope as one of your objective function. That is how we talked about the alternate solution in the graphical method. And the simplex method, the alternate solution happens when you find that one of the variable, for example here X2, which is in x2 is 0, which is in what? In the basis. Now, if we look on, if we look at x2, it is already here, which means irrespective of where it means when we can take x2 to, we can get multiple solution in our model. Recall that all basis variable must have a 0 coefficient in the objective function, right? Basis variable. So what was our basis variable? X1 and X2 could be our basis variable. And they must have what? Must have a coefficient of 0 in the objective row. However, in this optimal tableau, there is a non-basic variable x2, which also has a 0 coefficient in the objective function row. This indicates that bringing x2 into the basis will not change the objective function. So you see that x2 here have a 0. What happens if x2 is brought into the basis? The ratio test indicates, so if we're taking x2, we are there, we look for x2. Of course, the small number is here, so we're going to make this 1 and everything else 0 in that row. If you do that, what happens is we see, so of course this was already an optimal solution. We can read an optimal solution, z is equal to 280, and then x1 is equal to 2, and then x3 is equal to 8, and then x5 is 0, x6 is 0, x7 is 5, right? Now, if I change this as well, accordingly, even though it has a 0 there, I could still change by doing the row operation. By doing the row operation, what I get is, now I can have another solution where z again is 280, and then x1 is 0, x2 is 1.6, and then x3 is 11.2, x4 is 27.7, that's 0, that's 0, and that's 3.4. So you see that I get another solution. So of course, you see that the first optimal solution was 2, 0, and 8, right? 2, 0, and 8 from there. 2, so we have that, this one is a 2, this one is 8, and this one is 24, and 0, 0, and this is 5, right? So that the initial solution, so these numbers here, we have that x1, x2 is equal to that, and then we say x1 is equal to that. So these are, I can write this as a combination of my solutions, right? I.e., I can say 208 plus 1 minus this, which is 0, 1, 6, and that, and can simplify for this. So that's just what an optimal alternate solution look like. So just practice this. I will put more examples in the quiz. This week, by the way, you're gonna get a quiz where you try to solve some question. And I hope that by doing a lot of examples, you should be able to do the quizzes. Okay, the big M method, penalty method. So far so good. We managed all the questions we have seen so far. They were very well behaved, i.e., it was just less or equal, less than, and stuff. So what happened when you get things which are greater than, right? Or when we get something like with equality, what do we do? When you have an equation where, for example, we say x1 plus x2 minus x3 is equal to 5 instead of saying less than. So what do we do? In that system, then we must introduce a big M method to address that, right? So there is an example here where you see here now, remember we're going to have to introduce a minus and a minus here. So if we introduce a minus here, and then we won't get a basic feasible solution. Remember, we could read a basic feasible solution by reading what the slack variables are in our solution. Here we can't, because of course, here we will add x3, here we will minus x4, here we will add x, we don't have to add anything, it's already satisfied, so no addition. So when you write it, you should get this, right? But now we can read the basic, we can read our basic feasible solution here. There isn't. One here, what is it here? We don't know what, we don't have something where not everything else here is 0. Neither here as well, so that's a problem. So the constraints are not in canonical form, so it is not easily to find an initial basic solution. in the first constraint, x3 could be used as a basic variable, but there are no immediate obvious other for second and third. So what we're going to do is we're going to introduce the artificial variables that are labeled x1 and x2, which is here, here, and here. So that one already, because it was less than, we added x3 as our slack variable. This one, which didn't have, we're going to add artificial variable R1 and R2. And that then will give us, will be able, so now we know this is 1, everywhere else x3 is 0. Here R1, everywhere else is 0. Here R2 is 1 and everywhere else is 0, which means it's now canonical, right? Remember, canonical means that one variable holds a value of 1 and everywhere else in the other equation is 0. Here as well, R1 is 1 here and everywhere else is 0. R2 is 1 here and everywhere else is 0. So the system is in canonical, right? Now, from this constraint, the basic variable x3, x1 and corresponding basic solution and can easily be determined. Unfortunately, there is no guarantee that this, solving the problem with this constraint, the optimal solution which is obtained will be optimal solution to the original problem. If an optimal solution is obtained with the artificial variable in the basis greater than 0, then this will certainly not be an optimal solution to the original problem. Thus, it must be ensured that all artificial variables are non-basic, i.e. equal to 0 in the optimal solution. So in the optimal solution, we must make R1 and R2 equal to 0. To do this, this term is subtracted from the objective function for each artificial variable. Here M represent a very larger positive number. So we rewrite our equation now, but we introduce this in our constraint, right? We must take it away because it actually doesn't have any value than just helping us to formulate, to read the basic variable and move forward from that, right? So with this modified objective function, it's very costly for the artificial variable to be positive, and it will be expected that the optimal solution will have R1, R2 equal to 0. The optimal solution to the modified problem will then solve the original problem. If one of the artificial variable has a positive value in the optimal solution to the problem, then the original problem is infeasible, right? So we write it like that, and wonderfully we put it in a table like this, right? So of course this is not difficult. Again, now we want, because we are looking for a, remember our question was a maximization. We look for we first have to get rid of this. We must remove this from this part. Now, what do we do? How do we go about this? The first part is to take a row. It should be row 1 going to row 1 minus so it's going to be row 1 is equal to row 1 minus m row 2. And then again, we do that row 1 is equal to row 1 minus m row 3. So when you do that, which it hasn't been explained properly here, but you should know that what it's doing is taking row 1, which is m minus row. So the row operation is performed is row 1 minus m row 2, and again row 1 minus m row 3, and then you should get this, right? You should do that. After that, now we look for the most negative number, i.e. the most negative number here should be this, because of course, if this is the gazillion, 4 minus that plus that is become a huge gazillion. And then you look for the ratio. So of course, as usual, it's 4 divided by that, and then 3 divided by that, and this divided by that. So 4 divided by this, you should get that and this, right? And you should see that the smallest ratio is that, which means you're going to make sure that this becomes 1 and everything else becomes 0. So you do row operation again, and you should make sure that this is what you get, and then you do another row operation, i.e. what is the biggest number? The biggest number here is going to become what? Our biggest number is going to become this. This is a larger negative number. So if that's the case, everything's become 1, and and then the value become, this value has to become 0, everything else becomes 0. So this become 1, everything else becomes 0. So you do exactly the normal procedure. This is not an optimal W. Note that the artificial variable R1 has already been forced out of the basis. The next W is this, so this is an optimal W. So you do the other one and you should get this. You can write the raw operation on how this is done. If you can't find that, you should email me and we can discuss that. Okay, another one. So this is another example where we have, this is, you are adding, of course this is greater, so of course going to be minus again. We cannot read a basic solution. Remember, we say that our initial basic feasible solution cannot have negative numbers. From the initial part, that was an agreement. So you can't read as negative values, right? So you must then introduce R1 and R2 to make our solution canonical. And that's exactly what I do. And then now remember that this is a minimization. When it is a maximization, you should notice that we minused. When it is a minimization, we add, right? So my Z become this, it's not minus. When I rewrite, these are negatives, right? Okay, so I added here my artificial variables, and then what happened? And notice that in my example, I don't have any other variable. I have here, I added R1 and I added R2. There is no X3 like here. Why? Because X3 here was a result of it coming from being added here. But for me, I didn't have that. So I only had greater or equal two constants greater or equal. So it means my bases now are going to be my artificial variables R1 and R2. If I can get rid of them out of here, I get a good solution. Again, I explained to you what you should do, that we want to make this 0 and that's 0 as well. So the first thing I do is R1 plus MR2 followed by that. And if I perform that, I get that, and I perform again, I get that. Now, after performing those two row operations, i.e. making these things equal to 0, now I can go to look for the most negative, the most positive, because I'm talking about minimization. If it was a maximization, I look for the most negative. So notice that. And then when I do that, I should be able to try to get rid of this. And so the smallest number is that. So everything else become 1, everything else becomes 0. Again, that's the case. And then I look for the next one. This is the case here. And after I do that, you see that what has happened, all the artificial variable I've got out of here. So that should be my solution, right? So again, there's another example. So I'm not going to go on all these examples because I put them there, and I spend a lot of time to make sure that they are well explained and well, every step is indicated. So I encourage you to try them, and if you get stuck, get back to me. I'm going to stop here, and I hope that you will practice all these examples, and if you get stuck, you can get back to me. Now, the quizzes will be based on this as well. Now, there is even an infeasible solution for a big M. So more examples are put here for you to practice. So I wish you all the best in your studies, and I hope that these examples and this work which you have done will be really useful in helping you try to understand the thing. So please try to follow through with the raw operation I've indicated. I think this is far better and it is improving. The quiz will be based on the simplex method part only, but we expect you to do the big M for the coming weeks. So I will discuss this again for a big M. There will be another added lesson for it. So have a wonderful day, and we can talk again. Thank you very much for watching, and hopefully you will be ready to study. And if you have a question, email me as usual. Okay.